Hello everybody, my name is Professor Soborno in Bari from Bari Science Lab, and today we're going to be looking at some more physics. So today we're going to be looking at resonance. So what is resonance? Well, let's first explore it by looking at, springs. So we know most springs execute simple harmonic motion, right? Talked about pendulums a while ago, but those don't execute simple harmonic motion. But because of one reason or another, whether it be air friction, air drag, or water, something's eventually going to slow down and stop, to halt the motion. So, how do we stop this devastating little rule of the universe? At least, how do we temporarily stop it? Well, look at Newton's laws for a second. There are 3 laws that Newton owes to himself. Let me just say it in this dog real quick. So, his first law, so we know his second and third law. So we know his second The first one, however, is the one that matters the most. Now, the first one, what is it? Well, it's about inertia and momentum. So, inertia and momentum are basically the values in which how much something wants to stay in its position, or for momentum, how much something wants to keep moving. So, inertia is how much something wants to stay in place, and momentum states how much something wants to move, keeps moving. So now, first law also states that nothing will interrupt something's path when it's initially moved unless another force is exerted on it. Now, by this definition, that means that air friction, air drag, or the friction caused by water will eventually stop it, since it has a force too. Very small one, but still one to be sure. So, let's hope my mic doesn't get dipped in water. So, that means that we need to exert a counterforce to get it back to its normal state. So that means that we can't really stop it, since every physical thing has friction. Even what you see at the smoothest of surfaces, like this whiteboard, for example, when you zoom in very, very tiny, there are little tiny cracks that cause some friction. Everything has friction. So, some have less friction than others, but everything has friction, guaranteed. And nothing can be frictionless. You can get really close to friction with things like ice. You can get really close to zero friction, but you cannot actually get zero friction. So, that means we need to exert some counterforce at the right frequency so that it keeps going on. Imagine a little kid on a slide. Now, imagine you're a father and you're pushing your kid on a slide. A very transparent one to be sure. So, unless your kid is a 2-year-old, he wouldn't want you just bobbing around, just jiggling around the swings. He would want you to push, get him back, push him, and then let him go. He doesn't want you to just, like hold him all the way. Unless he's an infant or a newborn. But newborns can't speak. You can override their wants. No, seriously, don't. It might lead to child loss. Now, you have to get just the right frequency of the swing so that your child likes their experience at the playground. Just like you have to get the exact right frequency to hit something and suddenly strike it down so that it keeps going again. So, now that's really, that's how we can imagine things. So, oh, hell no. Okay, at least that wasn't the bottle filled to the brim. So, that means you have to get the exact right frequency. And what's the frequency here? Well, it's 1 over the natural period of the swing, which is how much time it takes for your child to swing forward and then swing back and land into your hands. Now, just like a child on a swing, things like this, if you give too much frequency, like this, if you give too much frequency like this, then it will just wiggle around, bob, and not really care too much. So, if you get just the right frequency, it has the maximum force and it just pops off a little, pops off wherever it's standing. Of course, you can't get the right frequency so your child pops off the swing. Not going to cause him to have a very fun time at the playground, rather have some very fun time with a lot of injuries. So, Tom Cruise style. So, yeah. That's most of what we know. So now, different objects have different frequencies. Like the example I'm going to be showing right now. Didn't keep these bottles to drink when I'm thirsty, despite how it may seem because I got angry that the water spilled. Okay. What I'm really here to do is show you the difference between the high frequency and low frequency. Let me blow into this bottle with gentle. Sounds kinda high, not in the alcohol context. Yep, that sounds pretty low. So you can see that the one filled had a very higher frequency than the one that was, just almost empty. So this shows that different objects can have different, resonation frequencies. So now. This is, no. So the thing is, remember what I said earlier? Well, things max out, things peak when the maximum velocity right at W naught. So this one is slightly less damped. And this one is the least damped.
Okay,
or maybe in reverse video, coincidentally. Thank you everybody for watching, and I'll see you next time. This video was sponsored by Brilliant.